Hello there, and welcome to another episode on our LTSpice tutorial series. So, we're following up from the previous video with the same circuit, and I'm just gonna give a recap. So, essentially, we learned about how to use the voltage control switch to be able to decide when a switch closes so that we can perform analysis, right? And so we probed here and we saw that, of course, a constant DC 5 volt was coming in, and then we also probed the current, and then we saw that for some reason current wasn't flowing until after the 5th second. I said for some reason because we know the reason. The reason is because the voltage that controls this switch turns on only after the 5th second, and so we see that no current flows until after the 5th second when it begins to flow. In this video, I want us to learn about another dot command or directive in LTSpice that helps you to measure quantities that you are interested in at specific times within the simulation. Apart from taking instantaneous measurement, this command also allows you to perform some calculations like average, max, minimum, integral, and peak to peak and stuff like that. Remember that LTSpice is powered by Spice, and Spice is a mathematical engine, so don't be surprised about all the kinds of mathematics you can do in LTSpice. So I'm going to close this, and the first question I want us to answer is, what if I want to know how much current was flowing at time t0? Of course, it's simple, right? You can always simulate and then you check the current that is flowing and you look at a plot here, you can see. But it is not always this simple to tell from the graph, especially if you have some complex stuff going on and you are interested in the instantaneous value of a particular component current or voltage at a specific time within the simulation, and you don't want to look at it on the graph because it's not always easy to do that. All right, so I'm going to close this, and as always, you click the .t to add a directive. You can see comment here and you can see Spice directive. If you make it a comment, yes, it will show on your schematic, but it's not going to have any effect on the simulation. Okay, so we want to select Spice directive, and the directive I want to teach you about is called measure. You can actually type the full measure, or you can just do MEAS. I'm going to type the full one again because I am pedantic. And once you've typed the dot measure command, you need to also tell what kind of analysis is happening and where the measurement is being taken. It's important, even though it is optional, but some commands that follows the expression are also specific to the kind of analysis that you perform. Okay, so develop this habit of always mentioning the kind of analysis you are performing. So dot measure, I'm doing a transient analysis, and let's say I'm interested in the current when the switch is off. So this I off is a store of the value of the expression that follows, right? So I'm going, what I'm saying is that I want you to measure something and store the value of this snapshot in time that you are looking at in what is known as I off. So it's basically up to you to choose something that is descriptive, right? And after that, you need to say find. So sometimes you can even capitalize this place so that, I mean, it's obvious which ones are from you and which ones are from LTSpice. You can also capitalize this, but anyway, not case sensitive. So I'm interested in the current. So to do current, you do I and then R1. So I'm interested in the current that is flowing through R1. So this is where the component designators are also important, right? So I'm interested in the current that is flowing through R1 at what time. So then you say at, again, I'm going to capitalize it, not because it matters, but I feel it makes it look cleaner. So I'm measuring the current at time 0, and I'm storing it in I off. And the reason I'm calling it I off is because based on this circuit that we've captured here, I know that because the voltage that controls the switch turns on only after the 5th second, at time 0 the switch is open, and so I'm measuring the current when the switch is off. That is why I call it I off. Like I said, you are free to choose any name that is descriptive enough for you. And as always, you need to drop it somewhere on your circuit. And now I can go on to simulate. And then you might ask yourself, okay, you've simulated, but how do you see the value of I off as you specified? Here you have to click on view and check the logs of the simulation. So you go to Spice output log. If you come here, you expect to see the name you gave to hold the value of the expression. So it is telling me that I off is equal to, this is 0.11 more zeros before 99. So essentially it's 0. It is telling you that at time 0 the current that is flowing is 0. Okay, so let's go and add some more measurement so that we learn different things. Okay, all right, so now we know when the current is off at time 0. Now let's measure the current at time is equal to 6, which is after the 5th second when the switch has been turned on. This time around, I'm not going to do the full measure thing, just to prove to you that it also works. And so I say tran, and then I'm going to call this I off. So I off, and I want to find the current that is going through R1 at time is equal to 6. All right, so that one we call it I on, because I wanted to call it I on, but I wrote I off. So let me fix that. When you right click, you can see that it gives you this GUI. You can actually make all the changes here, or you click cancel and then it takes you back to where you can type. I'll show you how you can make the changes using the GUI. Okay, so I'm going to change this to I on for current that flows when the switch is on. Okay, and I'm going to simulate this. Again, you go to view and you check Spice output log, and you can see that when the switch is on, because I'm looking at time 6, the 6th second, which is after the 5th second when the switch has been turned on, then we have 0.00. If we round this off, this is 0.005 amps, which is equal to 5 milliamps, just as we see on the plot here, that 5 milliamps is flowing. Okay, so these are two simple ways of taking measurements. Let's try some other ways. So what if I am interested in knowing the power that is flowing through the resistor when the switch is on? Okay, so let me close this so we have more screen real estate, and I'm going to click here, and what I'm going to say is I want to measure. So this time around I'm doing the full measure, and I am interested in, let's say, power through the resistor. Okay, so like I said, it's up to you to choose descriptive names, and I'm interested in power, and you know that power is equal to voltage times the current. Again, remember that Spice is a maths program, so don't be surprised that we are doing maths in here. Okay, so what's happening is I'm saying I am interested in finding the voltage VCC multiplied by the current that goes through the resistor at time is equal to 6. So I'm going to put this here. Let me zoom out a bit so it is much clearer. So I'm interested in this expression, the voltage here, because this is the only component in the circuit. It's just a resistor connected to a 5-volt source, and I'm interested in knowing the power that is being dissipated. Okay, and I'm interested in it at time is equal to 6. So this is after the switch has been turned on, and so I expect that current is flowing. So we simulate once again and we check the logs. Now if you check the logs, you can see that the power through the resistor, again, is a name you choose for yourself, so you make it descriptive, is equal to 0.025 if we round it up here. So 0.025 watt is what is being dissipated through this circuit, and that is true. You can confirm that with Ohm's law. You can either do V squared divided by R, which is 25 divided by 1000, because 1k is 1000, then you're going to get 0.025. okay, or you can also use the current version of the formula to confirm that indeed this is working. So apart from this, we can also do other things like what if I want to know the minimum power and also the maximum power. Okay, so what I'm going to do is I'm going to close this once again, and then I'll come here and then we do dot measure again. Sorry, let me position something well. So we do dot measure, and then I want to call this power max. Okay, let's do power main first. So the minimum power, and again remember there was a time when the switch wasn't closed, so at that point we expect power to be 0, right? So power main is equal to the minimum when voltage VCC times the current that is going through R1. And at this point I'm not specifying any time, so this command has different formats and you have to read the help to be able to understand the different combinations that are acceptable and also possible. But I'm saying I am interested in measuring the minimum power dissipated, and I'm going to store that in power main. So it's going to calculate this across the simulation and then it'll tell you what the minimum was. Okay, and I will do the same for maximum. Okay, so I'm going to put this one here, then I do dot measure I'm going to do power max, and I want the maximum of voltage in VCC times the current in R1, and I'm not specifying any time, so I'm going to put that one here, simulate, and I'm going to check the logs. So indeed you can see that power minimum is 0, right? This is 0.00, like 11, so 0.10 more zeros before these numbers come, so that is essentially 0. And the maximum power dissipated is 0. So it's basically the same value that we calculated here, and this occurs when the switch is closed. Apart from max min, you can do other summing or reduction operations. So I'm going to right click on this so that it will give me that UI I was talking about, and you can basically do the same thing from this UI. So what if instead of Okay, let me explain this. So it tells you applicable analysis. This is where you choose the kind of analysis you are doing. We are doing transient, and the result name, this is where you want to store the value that is being measured or calculated. The genre is what kind of operation are you performing? So we've done find, we've done max and min. Let's try average. But as you can see, there's also the derivative, there is peak to peak, there's RMS, there is integral. We will talk about all of these when they become necessary. So let's see average power that is being dissipated, and we expect that the average power is not going to be equal to the maximum, because at a point that between the 0th second and the 5th second, the power that was dissipated was 0, and then from the 5th second to the 10th second, the power being dissipated is 0.025 watts, as we saw in the previous simulation. And so when we average these out, it should be less than 0.025, right? So I'm going to click OK, and then you can see that it has changed. So you can either modify it by typing the command yourself, or you can also use the GUI to help you out. And I'm going to simulate this once again. We go to view and we check the Spice output log. I should have changed the name. This is average, right? So the average is 0.012 and the maximum is 0.024. Like I said, you don't expect the average to be equal to this. It shouldn't be equal to, neither should it be bigger than, because at a point it was 0, and all those zeros are going to cancel out some things that could contribute to the average. All right, so play with this, try build your own circuit and try to take some measurements until this makes sense. For now, you might struggle to see when this becomes useful, but as we get into more complicated simulations, you will begin to appreciate the capability to take a snapshot at specific times within the circuit instead of depending on the plot out here, because you aren't always going to be able to eyeball things correctly to see what you expect. Thank you very much once again for watching this, and I will see you in the next video.